In this video, we're going to start considering applications of the definite integral, and in particular, we're just going to outline some of the key terms that we're going to need, especially with regards to motion, so position, velocity, acceleration. And so I have a little summary box here that we'll take a look at. So first, this concept of displacement, for those who take physics, you should recognize it. It's a change in position. So usually it gets a triangle, or it gets denoted with a triangle, something like change, or delta, I should say, change in distance. Okay, so that's a net change in position. And what will accumulate that in calculus is the definite integral of your velocity function. Okay. Remember, the definite integral collects net area, so it counts area with curves above the x-axis is positive and below is negative. And then it'll give you like the net sort of the net area in total. Let's just do a little unit analysis as another way of understanding this, because this can be very helpful in other contexts where you're not familiar with the units. But velocity could be measured, for instance, in something like feet per second, right? So if velocity was measured in feet per second, it would be multiplied by this change in time, which would be seconds. And so notice, remember, the integral sums things, right? These are all like areas of all these rectangles. So it sums up feet. So this would accumulate a change in position, and of course the units would be feet. Okay, so that's displacement. That's just the integral of your velocity function. Now sometimes we want not the net change in position, but the total distance traveled. It's the difference between running around a track and asking what your change in position is. One lap would mean your change in position is 0, right? You're where you started. But of course, you'd be exhausted, so you actually traveled a distance. We would want to count that 400 meters as positive. So distance traveled is a counts all, right? It counts all distances, or all change in positions as positive. I'm just going to note that. Counts all change in position as positive. Okay, which means it makes no distinction between velocity being negative and positive. And the concept that does that is speed. So speed is a scalar, not a vector. So speed just has a quantity, and it counts everything as positive, potentially 0. And in any case, the way to effectively make sure that you are summing all areas positive is to put absolute values around your velocity function. Okay, so distance traveled is going to be the absolute value of velocity, the definite integral of that. All right, and then a change in position, or your position at any time here. We're going to look more carefully at this below, but your position at any time is where you start, okay, plus how you change. So I kind of don't like this double equal sign. I'm just going to change this. Focus your attention mainly here, okay, which I'll indicate below as well. But in general, what this is saying is that where you are is where you start plus how you change. Okay, where you are is where you start plus how you change. You should recognize this as being a rearrangement of the fundamental theorem. So let's just take a look at this and rearrange it. Okay, so if I rewrote this equation instead by putting my velocity function here, then if I subtract this term from both sides, what I end up with is S of B minus S of A. And this is just the fundamental theorem in a particular context, right? And that's because position is the antiderivative of velocity, right? We know that S prime of t is velocity. So this is just the fundamental theorem. And the College Board, for those who are watching with the AP exam in mind, the College Board loves to rearrange the fundamental theorem in various ways to see if you can analyze it in multiple directions. Okay, so that's your position. Your position is where you start plus how you change. So we can also think of our position function. So all I've done here is replace the b with a t so that we know at any time, at any given time, we can find our position. And so a nice sort of verbal scaffold is to think your position is your start plus your change. Okay, your position is your start plus your change. And again, we could always rearrange this to recognize the fundamental theorem. Okay, just as a one last note. Okay, again, that's just identical to what I wrote above. It's identical to what I wrote above, except we have our we have t instead of a. And of course, you could go one level down and make the same type of expression. So here we're saying your velocity at any given time is your velocity to start with plus your change in velocity. And so let's do a little unit analysis here while we're at it. Right? What could velocity be measured in? Well, it would be measured in feet per second. So your feet per second would be your units for velocity. So your starting velocity would also have feet per second. And then we just got to make sure this integral on the right here ends up having units feet per second, right? Because you can only add quantities with the same units. Now, acceleration has units like feet per second squared. Okay, but you're going to multiply that by a change in time, which would have unit seconds. And crossing those off, you'd be summing up, or the integral would sum up in the end velocity. And so therefore we have our change in our actual velocity by adding the start plus the change. And one last time, let's just note that a rearrangement of this could produce the fundamental theorem with different, different characters, but same concept. So subtracting this VA from both sides, we could rearrange it and say this. And of course, this is the fundamental theorem because velocity is an antiderivative of acceleration. Okay, so that kind of outlines the key ideas here. We have displacement, a change in position. The definite integral just accumulates that itself under velocity. Your distance traveled will require you to put absolute values around velocity so that all change in position gets counted as positive. Our position at any time is where we started plus any change. Basically, your position is your start plus your displacement, right? That's another way of thinking about it. I shouldn't point that out. This here is just your displacement above. And of course, you could make this, you could use other context, right? Your velocity is your starting velocity plus your change in velocity. The amount of people waiting in line at a concert is how many people started plus how many people entered over a certain time interval. Entered plus, and maybe subtract the people who left. But in any case, this process of setting up these integrals to model a situation is what this section's all about. And we'll do more concrete problems in a different video.